video, we're going to look on axial loaded members. We're given a problem. AC is held between rigid supports A and B. The cross-section areas in the left and right hand part are 1800 millimeters squared. This is the left part. 1200 millimeters squared. This is the right part. The modulus of elasticity, which is E, is equal to 6 giganewtons per square meters. And the coefficient of thermal expansion are given, which is alpha. It's 100 times 10 to the power negative 6 per degree Celsius. So the question continues. The bar is subjected to uniform temperature increase of 50 degrees Celsius. So I want to find the axial force in the bar. After that, we're going to find the max stress in the bar and also find the displacement of the point C. Before I do anything, I would like to list the numerical data that were given. So we're given E, which is the modulus of elasticity, and this is 6 times 10 to the power. I'm going to change giganewtons to newtons. So giga, that is times 9 per newton per meter squared. Okay. Then we're given the thermal expansion, coefficient of thermal expansion, which is 100 times 10 to the power negative 6 per degrees Celsius. We're also given the cross-sectional area of the left part and the right part. So what I'm going to do, I'm going to call this part 1, the left hand, and call the right hand part 2. So I'm going to say A1, which means it's going to be the cross-sectional area of part 1. That is going to be 1800 square millimeters. And for A2, which is the cross-sectional area of the second part, is 1200 square millimeters. And we're also given the length. So you can see the length from here to here. I'm going to call L1, the length of the left part, which is 600 millimeters. And also given the length of the second part, which is the right part, which is 300 millimeters. And also given the temperature change, which is going to be change in temperature, which is 50 degrees Celsius. If you understand the question correctly, this bar is held by rigid support. That means these bars are not moving. Okay, so what I'm going to do, I'm going to draw a free body diagram first. So the free body diagram is going to be, what's going to happen? We know that this bar is not moving. So that means there's some external force which is holding it. So what do we have? We're going to see, since it's not moving, we're going to have a reaction. We're going to have a force here, which is going to push it. The reaction force, I'm going to call it RA, and also going to have an opposite direction. Since it's constant, it's static, we're going to have an opposing force from Newton's third law of motion. So this one is going to be RB, and we still have our length from here to here, L2 from here to here. Okay, and this is said, we call this one part 1, and this one part 2. Okay, so from here I'm going to apply the equation of equilibrium. Since I know that this bar is not moving, I'm going to write the equation of equilibrium. So how many forces do we have? We have RA direction here, and we have RB direction here. So that means I'm going to resolve along the x-axis. So that means the total sum of the forces which are acting on the x-axis, and I'm going to take the right side as the positive, should be equal to 0. So what do we have? We have RA, and since RB is acting on the opposite side, I'm going to write negative RB, and this should give us 0, meaning RA is equals to RB, and I'm going to call this equation 1. But the problem with this equation, as you can see, we have 2 unknowns but only have 1 equation. So this is a 1 degree statistically indeterminate equation. So what we're going to do, we're going to choose between these 2 unknowns. We're going to choose only 1 unknown and use superposition of 2 determinant equation to find another equation, which is the equation of compatibility. Okay, so what we're going to do, I'm going to write what is going to happen here. So this is the free body diagram before anything happens. But what is going to happen next? What's going to happen is that we're going to have a constant temperature change. And after having a constant temperature change, this bar is going to expand. Okay, so on expanding, you can choose the side that you want. But in this question, I'm going to make RB the redundant, meaning that it will be no longer in use. So I'm going to remove RB. So when we do that, the reaction RA is going to be there. And this one is still part 1, and this one is still part 2. This one's still L1, and this one is still L2. Okay, so if we remove the support here, that means this bar will no longer be held by something here. That means it will be suspended. So it's going to have a force, and that force is due to the load. So what is going to happen if we apply it? This bar is going to expand, and it's going to expand due to temperature. So this expansion, we're just going to call it the expansion due to temperature. That is what is going to happen. But at the same time, since we say that we no longer have support here, RB, or the force due to the load of the bar is going to expand, but it's going to have some stress on it. So I'm going to put back the redundant, and this one is going to be RB, which is the redundant, because it no longer has support. So it's going to expand due to its load. So I'm going to say the expansion due to the load. I'm going to call it RB, which is the redundant. So we're going to use this information to find the axial force in the bar, which means that the force direction. Okay, so now let's do the work. We have this one equation. Okay, so from here, from number 3, right, I'm going to write from diagram 3. What do we know? We have a temperature displacement relation. I'm going to write it as temp displacement relation that we have. We know that when we hit a board or a solid, it's going to expand. And the expansion, or the length of the expansion, or the displacement of the expansion, which I'm going to call delta T, is going to be given by alpha, which is the coefficient of thermal expansion, times the change in temperature, and I'm going to multiply that by the length. That is what we're going to, that's what we know, meaning this bar is going to expand. Okay, so when it expands, what is its length? We know that we have L1 here, from here to here, and we have L2 from here to here. But we're applying the temperature on the whole bar. So that means the length is going to be this portion plus this portion, the length of this portion plus the length of this portion. So that means the change in temp due to temperature, the change of length due to temperature, is going to be equal to alpha times change in temperature. And I'm going to write L1 plus L2. We can just find the change of length due to temperature of part 1 plus the change in length of temperature of part 2, and add them together. But the other way that you can do is just to do the shortcut. Okay, and I'm going to call this, let me just call it the second equation, since I said this one was the first equation. Now let's go to diagram number 4. From D4, so this is for the diagram that we have said. This one's 2 part 1, this one's 2 part 2, and here we have C here. Okay, so on C we have another relationship that we have the force. Let me just write the force displacement relation. Okay, so from the force displacement relation, know that the change in length due to a force is going to be given by magnitude of that force times the length divided by E, which is the elasticity, times the cross-sectional area. Okay, so from here, what is our force? We can agree that our force here is the redundant, which is RB. So I'm going to write the change of length due to RB is going to be F, which is the force, and the force is RB times what is the length. Okay, so on the length, remember we have part 1 and part 2. Okay, so I'm going to first start by writing the change of length of the first part. So it's going to be RB times L1, and we're going to have E. See, the modulus of elasticity is the same, just going to be E times the cross-sectional area of part 1 plus RB times L2, which is the length of the second part, times E, which is the same, and the cross-sectional area of part number 2. And I'm going to call this equation number 3. So now we have 3 equations, but there is something that we have said. I've said that we have introduced the redundant so that we can use the superposition to find the 2 determinant equation, and those 2 determinant equations are going to help us to find the 4th equation. It's going to be the equation of compatibility. So the equation of compatibility. Okay, so for the equation of the compatibility, we know that this bar is rigid. So the net change in length of this bar will be equal to 0. Okay, so what does it mean? It means this bar is going to change due to temperature, going to be changed due to the temperature, and it's also going to change due to the redundant force, which is RB. So I'm going to write plus RB. So if we add this for this two lengths together, since it's rigid, we should get 0. So that means RT should be equal to negative delta B. Okay, and that is going to be the fourth equation. So now we have enough questions to solve or to find any missing information that we need. Okay, so what I'm going to do, I want to first find the axial force, which I've said just the force of the support or the reaction. Okay, so I'm going to use equation number 4. Okay, so from number 4, we know that the change in length due to temperature is going to be equal to the negative change in length due to R, right? So I can just put the negative here and just write the change in length due to RB, direction at B. Okay, so from here, what do I know? So the change in length due to RB, I have it here. You can see we have RB here, we have RB here. Also we have E and we have E. You can just factor out RB over E, the modulus of elasticity, right? And I'm going to have L1 over A1 here plus L2 over A2 right here. What about here? Negative delta T. Negative delta T, we have it right here. So it's going to be negative, and we're going to have alpha, change in temperature, and we have L1 plus L2, right? Let me just write it clear here. Alpha delta T, L1 plus L2 is going to be RB over E times L1 A1 plus L2 A2. Okay, so now I have to make R surgery of the formula RB. So RB is going to be, I'm going to multiply both sides by E. So I'm going to have negative alpha delta temperature. I'm going to have L1 plus L2 times the modulus of elasticity. And I'm going to divide both sides by this. So this is going to be L1 over A1 plus L2 over A2. And from here, I can put my values. We have the negative right here. And we have alpha. What is alpha? From the numerical data that we have is 100 times 10 to the power negative 6 per degree Celsius. Times the change in temperature. We know that change in temperature is 30 degrees. So I'm going to write 30 here. Now I'm going to multiply that by the length. So on the length, as you can see, our modulus of elasticity in terms of meters, and our area in terms of millimeters, and length in terms of millimeters. So I'm going to change everything to standard form. I'm going to change everything to meters. So on the length, I'm going to have 600 millimeters. If I convert it to meters, I'm going to multiply by 10 to the power negative 3. For changing millimeters to meters, so I'm going to write 600 plus the length here, which is 300. Now I'm going to multiply that by 10 to the power negative 3 meters. Okay, times we have E here, times 10 to the power 9 Newton per meter squared. So L1, we have 600 millimeters, 600 times 10 to the power negative 3 meters. And I'm going to divide this by the area. So area we have 1200 millimeters squared. So we know that 1 millimeter is going to be 1 times 10 to the power negative 3 meters, right? That is 1 millimeter. So if you say 1 millimeter squared, that's going to be 1 times 10 to the power negative 3 meters times 10 to the power negative 3 meters. So we're going to multiply 1200 meters times 10 to the power negative 6. First, from here, I can add by the laws of indices, meters. I'm going to write plus. And now for L2, which is 300, which is 1200, 300 on top, 300 millimeters times 10 to the power negative 3 meters divided by 1200 meters times 10 to the power negative 6 meters. So since it's the area, we have to put squared right here. We're going to get 462857 5 over 7 newtons. And I'm going to leave it as a fraction since I want to use it to calculate the stress and the strain. So this is RB, and we have a negative sign here. So So the negative sign, what does it imply? We have said when we set our redundant, we say that our redundant is going in this direction, but from the first diagram, we have said that this force is a compressive force since it's keeping this bar in contact. So that means RB, or the force, the force direction, which is RA, which is said is equals to RB, is equal to 46,28557 newtons, and I'm going to write C to indicate that it's a compressive force. But remember, when we want to calculate something or use this force to calculate, we're going to put the negative sign, right? So on the second part, we want to calculate the maximum stress. That is going to be part number 2. So for the maximum stress, normally what you have to do, you have to calculate the stress of this first part and the second part. But when you're an engineer, I think you have to know that the region with the thicker or with the small cross-section area, that is the region with the maximum stress. So I'm going to save time here and just calculate the stress of the second part. So I'm going to write the stress of 2 is going to be, that formula of stress is going to be force over area, and the force is equal to this one. And if you write this one as a fraction, you're going to see that it's going to be 324,000 newtons divided by 7. And for the area, cross-sectional area of 2, let me just write 2 right here to indicate that it's going to be the area of the second part. So it's going to be 1,200 times 10 to the power negative 6 meters squared. And if we do that, you can calculate, you can get, it's going to be 38, and here we're going to have 571 4.28.57 newton per meter squared. Okay, so to simplify this, just write it, let's change it to mega, since you can see this is 38 million, so I'm going to write this as 38.57 mega pascal, right? And now for the last part, which is the displacement of point C. Okay, so what is going to happen is this. So when this thing expands, we have said this is point C. When this thing expands, point C is going to move a little bit. We have to agree. And after that, it is also going to move due to the combination of this force RB. But in this case, it's going to be the expansion of RB due to its load. So that means if we add those two displacements together, we can calculate how far C has moved. Okay, so let's do that. So I'm going to say the displacement of point C is going to be the displacement due to temperature change. So that is alpha times the change in temperature of A1. Okay, so say this is point C. Since say this is my positive x-axis, I'm going to say point C is going to move going into this direction, plus the change due to RB, and you know that the change in length due to a force is equal to FTA force, and in this case force is RB times the length, which is A1, over E times A1. Okay, so from here we have negative 100, it's not negative 100, it's positive 100 times 10 to the power negative 6 per degree Celsius. Okay, and I'm going to write times change in temperature, which is 30, times the length, and the length is 600 times 10 to the power negative 3 meters. Okay, that is for the first part. And for RB, we're going to put a negative sign here since we're now considering the direction. This is displacement. If we ignore this negative sign, we'll get a wrong answer. So I'm going to write plus negative. And for force, we have 324,000 over 7 newtons. Now I'm going to multiply that by the length, which is 600 times 10 to the power negative 3 meters. And we're going to divide this by E, and our E, 6 times 10 to the power 9 newton per meter squared, times area, and you say the area is 1,800 times 10 to the power negative 6 meters squared. The change in temperature is 50, so this should be 50. Okay, and right here it's 50, and the answer here is going to be negative 0.0004.28 meters. And we're going to write the magnitude. Let me just write it as a fraction. 3 over 700 7,000 meters. That is going to be the final displacement. So the negative is just showing us that it's going in the left direction. That's going to be changed in treatment of C. It's going to expand. It's going to be out back. So this one is just for the direction. Okay, so the other thing that you have to do is just to cross check my calculations with yours. Thank you for watching.